Okay, so there's some properties of sound that you need to understand in order to understand how it propagates like a wave. One is that we kind of know how fast it moves when it's moving around in the air. It tends to move, on average, around 1,130 feet per second. For the metric inclined, that's 344 meters per second. But for purposes of this class, we're going to mostly stick to feet. And that's not just because we're in America. It's because the math is easier in feet than it is in meters, for reasons you will see. Because 1,130 feet per second is actually not all that different from 1,000 feet per second. And you will find, through a lot of the things we talked about, that in sound, close counts. Okay? There's a pretty wide margin of error for a lot of the things that we do. Not everything, but a lot of the things we do, pretty wide margin of error. And functionally speaking, 1,000 feet per second and 1,130 feet per second, for most of the situations where you have to care about the speed of sound, either of those values is fine. However, the speed of sound is a bit of a moving target. That 1,130 feet per second is an average, actually, because sound will travel at different speeds depending on things like the temperature of the air. So sound moves faster as the temperature increases. Okay? And air pressure, like the atmospheric pressure, has an impact on how sound travels. Humidity has an impact on how fast sound travels. And so it changes depending on altitude. It affects how quickly sound moves. So, for example, I have found that here in Winston-Salem, North Carolina, on most days, sound travels 1,050 feet per second. I know this because I've measured it. And it just is. That's just how fast it moves in this town. 1,050 feet per second. So you have to kind of, if you want to get really specific, it kind of depends on where you are. Okay? But there will be times we will do math that will involve the speed of sound. And sometimes I'm going to want you to use the 1,130 feet per second. And sometimes I'm going to want you to use the 1,000 feet per second. And the code word for knowing the difference is when I say, let's figure this out in our head. And when I say let's figure this out in our head, that means you use 1,000 feet per second. Because 1,000 is a much easier number to do math on in your head than 1,130 is. So when I say let's do that in our head, use 1,000 feet per second. When I say let's use our calculator for this one, let's use 1,130 feet per second, because that's more accurate for most situations. Okay? How we doing? Everybody with me so far? Great. Okay, well, so that's about speed of sound. And so here's what happens. When we say it moves that fast, what's really happening here? Well, sound is made by doing what's called compression and rarefaction of the air. So air, we usually can't see it. But if we could see it, we would see that there are these little air molecules that are sort of suspended. Yes?
Refraction or rarefaction?
Rarefaction.
Okay.
Did I pronounce it wrong?
I don't know. I think you pronounce it like refraction.
Okay. So there's these air molecules that are kind of like hovering in the air, and they are kind of, they have a default state, right? They kind of, unless they're acted upon by some other force, they're going to be in this place they're going to be. okay? But they are not like locked to that spot. Like they're elastic to some extent. They will move a little bit, okay? And so sound happens when you, a compression would be when you squeeze those air molecules together, closer together. And a rarefaction is when you stretch them apart, okay? Now, when you do that in a pattern, squishing it together and pulling it apart, and you do that over and over and over again, if you do that fast enough, then there's this little thing in your ear, some call it the eardrum, or the tympanic membrane. What that thing does is it responds. Because when you're compressing that air, that increases pressure, and that actually pushes on that eardrum. And then when you stretch the air molecules out, it pulls at that eardrum. Okay? And as you push and pull at that eardrum, it allows your brain to interpret sound. Okay? So the rate at which you are compressing and refracting is what determines the pitch of the sound or the frequency of the sound. So by pitch, we mean, is it a really high frequency sound or a low frequency sound? Is it a high sound or a low sound, right? Sometimes that's described as pitch. We will mostly describe it as frequency. And frequency is how frequent is that cycle of compression, refraction, right? How frequent is that? And we tend to talk about it in terms of cycles. A full cycle is one compression, one refraction, right? You do one round of that, that's a cycle. Now, we measure those cycles, we measure the frequency in hertz, named after a guy named Hertz. Everything in sound is named after the guy that invented it, okay? That's what happens. 100 years ago, there were all these guys that invented sound. And whatever part of it they invented, they named after themselves. And now forever, henceforth and forever, everyone has to say their name whenever we talk about that thing that they figured out, okay? Wouldn't that be great, right? So Hertz. There was this guy named Hertz that defined this, okay? And Hertz is cycles per second. How many cycles did you do in a second? In general, humans, which I think are all of us, our ears, on average, can convert 20 hertz into something that our brain would interpret as sound. And it can convert frequencies higher than that up to, on average, about 20,000 hertz. 20,000 hertz, we can interpret that as sound. On average, that's what the books will tell you.
Yeah.
But
one person can't hear that high, right?
yeah, in practice, it's not quite that wide, actually. There are very few people I've met that can perceive very much above 16,000 hertz. And you've all been doing sound, Jim, and you know kind of more or less what 16,000 hertz sounds like. That's a pretty high frequency. Much higher than that, and you can hear it if you really work at it, really pay close attention. You can kind of perceive that something's happening. If you're young and haven't damaged your hearing and all that kind of stuff. But for example, I mean, I'm in my mid-40s, and I've taken very good care of my ears over the years, but I struggle with hearing things above 16,000 hertz, okay? So just be aware that, this is an average. This range of human hearing was determined based on some research that somebody did a long time ago, and they kind of created an average of all the people they sampled. This is what they came up with. But it's going to be different for every person. Every person's range of hearing is going to be different. But also you have to think about what is, all we're defining really is, can you perceive it? There's no definition here of how well do you perceive it, right? It's a binary. You either perceive it or you don't when we define that range of frequencies. But if you include that variable of, well, how well do you perceive it, then it gets a little more complicated. All right, any questions about any of this? Sort of making sense? Okay, hopefully you've heard these kinds of concepts before. This is maybe you talked about this in a high school physics class. All right, this is an attempt at making visible the invisible. So I'm trying to show you what this looks like. So we've got this symbol on the left is a tuning fork. And a tuning fork is this little piece of metal that vibrates, those little arms on it. Wah, 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 wah. I push and pull on the air. And you can kind of see the air molecules getting squished together and spread apart. And that distance between the compressions is called the wavelength. That wavelength is figured out based on the relationship between the speed of sound and the frequency. So wavelength is the distance the sound travels to complete one cycle. And you can figure that out mathematically by taking the speed of sound and dividing it by the frequency. And you will get a wavelength. Okay? Now, I have drawn this little triangle in the bottom right of the screen. This is an example of a tool that I find is useful to help me do the algebra on this, because I struggle inverting equations and stuff like that. It's very difficult for me. But this makes sense to me. I don't know if you've ever seen this before, but I will explain it. So if wavelength equals the speed of sound divided by frequency, you could diagram that using this triangle. If you circle the thing you're looking for, which is wavelength, the things that are left are the C and the F. The C stands for speed of sound, F stands for frequency, and their speed of sound is on the top of frequency, which usually means you divide it, right? If you want to find out the frequency, you can circle frequency, and that leaves you with speed of sound on top of wavelength. So you would do speed of sound divided by wavelength, okay? If you want to know the speed of sound, because remember I said I measured the speed of sound, I figured it out. Well, how did I figure it out? Well, I would circle C for speed of sound, and I would be left with wavelength next to frequency. And when you put those two variables next to each other, that usually means you multiply, right? So that helps me navigate that little equation. If that's helpful to you, then great. But I will have that on there a lot because that helps me remember how to do that. Does that make sense? That work? Okay. So let's try it now. So no calculators yet. What is the wavelength of 20 hertz? Well, let's just kind of like talk through this. So I want to know wavelength, which means I need speed of sound divided by frequency, C divided by F. Okay, so I'm looking for wavelength equals C divided by F. Okay, what's C? 1,000 feet per second. So 1,000. What is F? Frequency, and what's the frequency?
20.
20. 20 hertz. So I'm saying, all right, this will be 1,000 divided by 20. Hopefully you can do that in your head. What's 1,000 divided by 20?
50?
50. Yeah. So, I mean, one way to think about it is 1,000 divided by 10 is 100, right? That's easy. And therefore, 1,000 divided by 20 would be 50. So it is 50 feet. That's the wavelength of 20 hertz is 50 feet. Okay, how was that? Did I lose anybody there? Yeah.
Okay, I get this, yes.
Yep.
But the breakdown of the 1,000 divided by 10, you say?
Mm-hmm.
Just to
100. 1,000 divided by 10 is 100. That's easier for me to understand, but maybe my brain's weird, so.
So then it would be 1,000 divided by 20, right?
Yeah. You don't have to think about it that way if that doesn't help. But, if you can just do 1,000 divided by 20 in your head and you get 50, then fine.
You know, I don't. That's why I was.
Okay. All right. Anybody else got any questions? Okay. Well, let's do another one. What is the frequency of a tone or sound that has a 10-foot wavelength? All right. Well, I want frequency, and therefore that's the speed of sound divided by wavelength. So the frequency is going to equal speed of sound divided by wavelength. Okay, speed of sound equals 1,000 feet per second. The wavelength is 10 feet. So this is 1,000 divided by 10 equals 100 hertz. How's that? Are you with me so far? All right, any questions about that?
No.
All right, let's go to the next one. What is the wavelength of 1 kilohertz? So 1 kilohertz is another way of saying 1,000 hertz. The K means 1,000, okay? So wavelength of 1,000 hertz. So I need a wavelength. So wavelength equals C divided by F. C equals 1,000. F equals 1,000. 1,000 hertz. So what is 1,000 divided by 1,000? 1, right? 1 of what?
Unit?
1 foot.
Okay.
Because we're doing feet per second in speed of sound. 1 foot is the answer. 1 kilohertz is 1 foot. Everyone follow that one?
Yeah.
Good?
How did we get to feet?
Feet is because the 1,000 for speed of sound is based on 1,000 feet per second, right? Okay, what is the wavelength of 250 hertz? I want wavelength, and wavelength will equal speed of sound divided by frequency. C equals 1,000. So that's just something you memorize. And frequency, in this case, equals 250. So that's going to be 1,000 divided by 250. What is that?
4.
4. Here's the rule, by the way, with math. It is not right until 3 people got the same answer. Okay? So even that includes me. So yes, I say 4. And I see 2 other people in the room that are saying, yes, 4. That means it's probably right. It's unlikely that 3 people would make the same mistake. It's possible, but not likely. Okay? So this would be 4 feet. 4 foot wavelength of 250 hertz. Yeah?
Yeah, I got it.
Okay?
Okay.
All right, you ready for the next one?
Oh, God.
What is the frequency of a sound that has a 5 foot wavelength? Frequency is I want. So frequency equals speed of sound divided by frequency. C divided by C equals 1,000. Frequency, or no, wavelength equals 5 feet. So this is 1,000 divided by 5, which is what?
200.
So I got 200 hertz. Okay?
Wait,
Yep.
so, hold on, I'm gonna write this in that.
Yeah. Taking baby steps here. It'll get harder.
We can stay here, that's
Yeah.
fine.
So
I'm happy here. Baby steps are good.
we did, we've been using the same like equation for, I guess, majority of these problems.
Yep.
But one of them, we did frequency equals C divided by percent.
Oh, I drew that
Speed of sound
wrong.
divided by wavelength.
Hang on, I did that wrong.
Okay, I was gonna say.
C
like,
divided by wavelength. I wrote that
Okay.
wrong. Sorry, my bad. Good catch. Okay,
So then what's the? Oh, never mind, okay.
alright, good catch. We good? Alright, we're done with doing it in our head. Let's do it with calculator.
I know.
So what is the frequency of a sound that takes 50 milliseconds to complete one cycle? Okay, well, we got a problem here. First is frequency. We understand frequency by taking the speed of sound divided by the wavelength, right? So frequency equals C divided by F. We don't know how to do this with time, right? Because I'm saying 50 milliseconds to complete a cycle, right? So we're missing something here. Okay, how can we go from 50 milliseconds to a wavelength? I did it again. Wavelength. How can we turn 50 milliseconds into a wavelength? Well, a wavelength is the distance that the sound travels to complete one cycle, right? Because that's what I just told you. So we're close. We know how much time it takes for it to complete a cycle. Can we convert that into a distance
Wait,
based on what we know about how fast sound travels? Yeah, we can. Now I'm going to teach you the convoluted way that I figure this out. And those of you that are good at math are probably going to go, Jason, come on. But this is how we're going to do it, okay? So we know that sound travels 1,130 feet per second. We're using that this time because I said use a calculator, okay? 1,130 feet per second. How many milliseconds are there in a second?
1,000.
1,000. Okay? There's 1,000 milliseconds in a second. If you didn't know that, I just told you. Okay? So I would sure like to know how many feet per millisecond is the speed of sound. That would be helpful.
1,130,000.
Well, no. If we are going to take this and we're going to divide it by 1,000,
Oh.
right? Because I want to know feet per millisecond. So if I have 1,130 feet per second, and there are 1,000 milliseconds in a second, then I can take that and divide it by 1,000, and I will have feet per millisecond, won't I? So what is 1,130 divided by 1,000?
1.13.
Well, let's do that on the calculator real quick here. 1,130 feet per second divided by 1,000. And I got 1.13. Okay? I know Eric got that. Did anyone else get that?
Yeah.
Yes, okay, that's right. So that equals 1.13 feet per millisecond. Okay. Well, I have 50 milliseconds. You see where we're going now? So I'm going to take 1.13
Are you gonna divide it?
times
Multiply.
50.
Multiply it.
Okay.
Okay. Okay.
And I will get
Okay.
This is like
the distance
Yes.
that the sound traveled
This equation.
over that 50 milliseconds, won't I? So what is 1.13 times 50?
56.5.
Times 50. I got 56.5 too. It must be right. Okay. 56.5 feet. Guess what that is? That's the wavelength. Now I can do this math.
Oh.
So,
Do the actual problem.
now I can answer the question. Now I have a number I know how to work with. Okay?
We hadn't even
So
started.
now I'm going to do speed of sound divided by that wavelength, which is 1,130 divided by 56.5. What is that?
Okay. 20.
So
Whoa, I hit multiply.
1,130 divided by 56.5. I got 20, which is 20 hertz.
Okay.
Look at that. Did anyone else get 20?
Yes.
Yep.
So there you go. That is the answer.
My brain just doesn't work that fast.
Okay. So why did we have to go through that whole convoluted thing? Well, because one thing you're going to learn as we go through this is you don't get to control what format the data gets presented to you. Okay? The manufacturer of the equipment is going to tell you the information that they want to tell you. And they are not going to tell you the information they don't want to tell you. They are going to try to paint their product in the most favorable light possible. And so they are going to only tell you about the good stuff. And they are going to not tell you about the stuff that doesn't look good for them or that doesn't fit their messaging about what their product is good at. And so sometimes you have to take the information they give you and turn it into the information you need. Okay? And this is a good example of that. Yes?
So if it was if it said it takes 1 second to complete, would you just do 1,130 divided by 60? Or how would you go if it was in seconds instead of milliseconds?
Oh, if it was 1 second to complete a cycle? Yeah, then it would be 1,130 divided by 1.
Oh yeah, because it would be in seconds. Okay.
No, would that be right?
Would it?
Yes. Yeah, that would be wavelength, which would be a frequency we can't hear. That would be like way, way down there.
So low you could.
That's a really long wavelength. Okay, any other questions from anybody else?
How do we get here?
Say what?
How do we get here?
So we started with this question that says, what is the frequency? So frequency was the thing that I needed to find out.
Right.
And the thing I was told is, whatever this frequency is, it takes 50 milliseconds to complete a cycle. So what I had to do was turn 50 milliseconds into a wavelength. Because I have to have a wavelength in order to find out a frequency.
Right.
So this whole right side of the slide is how do you turn 50 milliseconds into a wavelength? And once I had the wavelength, then I could do the math for frequency equals speed of sound divided by wavelength.
But this is using a calculator.
And this is using a calculator, so we're using 1,130 feet per second for the speed of sound.
Technically, since we already found
I wrote it all down.
the milliseconds, technically, if it was like the next question was 60 milliseconds, we would just have to do 1.13 times
Yeah.
60.
Yep, and this is a number you should memorize.
Like I'm going to go.
1.13 feet per millisecond.
Yes.
Just memorize that. Or if you're doing it in your head, 1 foot per millisecond.
Oh wait, so that's not per second, that's millisecond.
Yeah, 1.13 feet per millisecond.
Second. Okay.
Just memorize that. Sound travels 1.13 feet per millisecond, or 1,130 feet per second.
That.
Or if you're doing it in your head, 1 foot per millisecond, right?
Oh yeah, because then you don't have to do the first step
Yeah,
that
exactly.
you did. Yeah, valid.
Okay? And you will find that just doing 1 foot per millisecond, like if you're just doing a simple thing of like, how long is it going to take for the sound to go from the stage to the back row of the theater? Well, you can just measure that distance in CAD. That's the milliseconds. Ish. Pretty darn close. Okay? And close counts for sound most of the time. Okay, let's see. We're doing okay. We got a bit more time. What is the wavelength of a 20 kilohertz tone, a 20 kilohertz sound? Okay, so I want to know wavelength, which means wavelength equals speed of sound divided by frequency. Well, what's the frequency in this case?
20,000.
20,000 hertz, because remember K means 1,000. So 20 kilohertz means 20,000 hertz. So frequency equals 20,000, and speed of sound equals 1,130. So we're going to do 1,130 divided by 20,000. I don't know about you, but I cannot do that in my head. So I'm going to go over to the calculator. We're going to say 1,130 divided by 20,000. Oh, just lost my screen. Okay, there you are. Oh, did it just unmirror? I'll hit the weird button. Hopefully that didn't screw up the point. Okay, it was 0.056 or 0.0565. Right? Is that what everyone else got?
Yes.
Yep. So let me write that down over here. 0.56. Yeah. 0.0565 feet. Okay. Yeah? Very, very small.
And that's the wavelength.
Wavelength of 20 kilohertz.
Ah,
Okay? Get out at
yes.
3:20, right?
Yeah, 3:20, yes.
Okay, got 10 more minutes.
All right.
What is the frequency of a sound with a 7-foot wavelength? Okay, frequency equals speed of sound divided by wavelength. Speed of sound equals 1,130 feet per second. Wavelength, in this case, equals 7 feet. So this would be 1,130 divided by 7. What does that equal? Somebody do that math.
Asking too much.
I got
1,143.
Okay, I heard 2 people got that. Anybody else?
I
got
also
that?
got that.
Reese got that. Okay, must be right. So that is 161.43 hertz. Okay, everybody good? We got that?
Is hundredths usually plenty of?
Yeah, generally, I don't, for most situations, I don't need you to calculate any more than 2 decimal places. Very few exceptions.
Right. I guess the last problem was an example.
Yeah. We're talking about such a small value that it probably matters. But. Okay.
Do you round up or do you just like leave it?
So yeah, if you're going to, if you got something that has more than just 2 decimal places, you just follow the rounding rules. If the next value is 5 or higher, you round up. If it's less, you can round it. Okay. What is the wavelength of 3 kilohertz? Well, wavelength equals speed of sound divided by frequency. Speed of sound is 1,130, and frequency is, what is 3 kilohertz? 3,000 hertz. So 1,130 divided by 3,000. What is that?
probably a 0.3 something.
0.3.
Oh, I did it wrong.
Connor says 0.38.
I agree.
Seth says 0.38. Reese says 0.38. That's probably right.
Yeah.
0.38 feet. There you go. We did it. How many more of these I got? Got another one. Wavelength of 300 hertz. Okay, I want wavelength again. So wavelength equals speed of sound divided by frequency. Speed of sound is 1,130. Frequency equals 300. So 1,130 divided by 300.
3.77.
All right, I hear 2 people got that. Seth got that too? Okay, good. Probably right. 3.77 feet.
Yeah.
Did you get that, Desmond?
Oh, yes.
Okay. You were saying, wait, what?
Because at first I typed it in, but that's not what came up, but I typed it again, I must have hit something wrong.
All right, see, this is why we do 3 answers, right?
Nice. Well, for that problem, I don't think we need to do that much math because all we really need to do is just move the decimal down like 1 place.
Yeah, there's lots of shortcuts like that. Okay, here's a wild one.
Oh.
What is the frequency of a sound that has a 3-inch wavelength? Hey, wait a minute, Jason, we don't know how to do this with inches. Okay, well, using the strategy that we employed before when I threw milliseconds at you, can we use that same strategy to get us through this?
Theoretically.
Probably. So, how many, okay, let's do this the very long, slow way, okay? So, how many inches are in a foot?
12.
12. Okay. So if I have 3 inches, that is 3 inches out of 12, which is what I would need to get into the feet. So I could do that by saying 3 divided by 12, right? And what would that give me?
0.25.
0.25 feet, right? So 3 inches is 0.25 feet, right? Okay, well now I can do this. So frequency is speed of sound divided by wavelength. So that's going to be 1,130 divided by 0.25. That would be
4520.
4,520 hertz.
Yeah.
Otherwise known as 4.52 kilohertz. Just as a gee whiz, right? And sometimes you'll see on the homework I'm giving you, I will say whether I want you to give it to me in hertz or kilohertz. Okay, because that's how Canvas will know how to grade it. Canvas is going to grade it automatically for you. So you've got to make sure you put it in the right value. Okay. There you go. Either of these are technically correct, but depending on the computer you're talking to, it's going to want it in one of those 2 forms. Okay, here's that same question again. What is the frequency of a sound that takes 3 milliseconds to complete a cycle? Okay, well, we memorized something about this, right? We know that sound travels 1.13 feet per millisecond. Because I told you to memorize that, and of course you did, right?
Yeah, of course.
Already?
Of course.
What
do you mean?
So we can say, all right, well, we just take that times 3.
Yeah.
Okay, so 1.13 times 3, what do you get?
3.39.
3.39 is what Eric got. Anybody else get that?
Wait. I don't know.
Connor got that?
Yeah.
Anybody else get that? Kat got that? Sounds like? Okay.
Yeah.
All right, so what's that? What is that number? It's feet representing the wavelength, right? Feet as a wavelength, okay? Okay, great. Well, now I can do this. So this is speed of sound, 1,130 divided by 3.39. Give us a minute, guys. Hang on, guys, we're not done yet. So 1,130 divided by 3.39.
333.33.
Ah, look at that. 333.33 hertz. Okay, anybody else get that? Yes?
Yeah, I got that.
Yep. Must be right. 3 of us got it.
Okay.
I think that's the last one. Yes, it is. Okay, so we will pick this up
What was the
on
answer?
333.33 hertz.
Mhm.
Okay, you know enough now to do a few of those questions on the homework. So if you wanted to get started on that, you could. All right?
And you said like you can just go back.
Yeah, yeah. It'll save your progress.
Yeah, now about resonance.
Say what?
Can I get the next number? Yeah.
Resonance? We'll talk about that next week, or on Thursday. So this is where the rubber meets the road. We're going to understand why we just spent all that time understanding the relationship between frequency, wavelength, and speed of sound. And it's all about resonance. Okay? We didn't. I thought we'd get to it today, but we didn't. So I actually, next Thursday, I'm going to resonate this room with actual sound, and you're going to hear what that sounds like. Okay? All right, there you go.
I understood the math.
There's your first day.
Oh my god, look at me.
You did it.
Look at me. Go.